Okay, everybody, welcome to class. So midterm 3 was the highest scored midterm I've ever given since I've been here. So that was either too easy or you guys did phenomenally well in this last couple weeks in class. I'm going to go ahead and believe it was the latter. You guys just were amazing this last time around. Something like 30% of the class got 90% or better, which is bananas. So well done on that. I only had to apply a 2.5-point curve to it to bring it up to an 80% average. So the score that you see there is with the curve added on Canvas. You can pick up your exams anytime in my office. Let's talk about homework 9. One of the outcomes of this class, it says here, it has to have, people have to develop an ability to function on teams whose members have interdependent and complementary skills. And another one is, because you're engineers and you have to learn how to communicate as much as we'd like to just do our projects from our basements alone, you have to learn to communicate effectively in oral and written form. So homework 9, instead of doing book problems and PDF problems, it's a project. And here's the project. I think you'll like it, I know. I think it's not as terrible as you might think. You're going to grow between now and the last day of class, December 4th, the largest single crystal possible, right? So this chapter is talking about nucleation and growth, right? Part of that is growing crystals, right? So you're going to grow a single crystal. And I've got some tips. There's some great YouTube videos I'll point you to. You have to do this in a group setting. So your teams have to be between 4 and 6 people. And they must include somebody outside of your major, right? So if you're MSc, raise your hand. If you're mechanical, raise your hand. So you're going to have to mingle a little bit, right? So I will... if you need help finding people, I can provide a list of the names of the MSc people on Canvas or something. Otherwise, you're gonna have to talk to people and ask them what they study. Okay, here's what I'm looking for. This project, it will be due on the last day of class, which is December 4th. What you turn in ahead of time, it needs to be turned in the night before the PowerPoint so that we can watch them and grade them. Needs to be a 6 to 10 slide presentation, right, on how you grew a single crystal from a solid, okay? You can pick any material you want that you want to grow. I suggest something non-toxic and easy, like sugar or salt or Epsom, right? But you can grow whichever you want as long as you do it safely, right? You only have 3 weeks to do it. So as we cover things in this chapter, nucleation, we talk about what things lead to faster growth and transformation times. I suggest you put some of those ideas in practice. You might even want to try and grow 2 or 3 different crystals under different conditions, say temperature, concentration, stir rate. Those things will lead to different sized crystals. You can try a couple. It's not like you only get one shot. If you want to try a couple, try a couple. Pick things that are cheap. I don't expect you to spend any real money on this. You can buy all the salt or sugar you need for this for like $1 to grow these things, okay? This has the homework which will be posted after this class describes exactly what I'm looking for. For example, I want you every day or at least periodically, every couple days, to take your crystal out and measure it so you get a feel for how the kinetics are changing. The best thing to do would be to weigh it. If you have a little digital scale in your kitchen, that's the best way. You can also do it with length if you measure a length. But you have to report those every couple days, okay? I'm going to want you to draw the crystal structure in Vesta. I can help you do that if that gives anybody flashbacks of darker days. I can help you with that. It's pretty simple, actually. You have to embed audio in the PowerPoint presentation. If you've never done that before, I can help you with that. It's pretty easy. Make sure it's a single crystal, not a polycrystal. A single crystal, like if you've seen like these sugar candies at state fairs and stuff, this individual thing right there is your single crystal. But if you don't control its growth, you're going to get polycrystal, right? So the task that you have is to grow a single crystal. I'll send you a link to a good YouTube video that sort of explains how to do that. So I will post this, and if you've got questions, come to class next Wednesday with your questions. And you'll want to start growing your crystal next Wednesday. That will give you a full 3 weeks to have it grow. If you want to start sooner, by all means, go for it. The team that grows the biggest single crystal, in addition to fabulous prizes, which I will make available, and you don't want to miss these, I will drop an extra homework, right? I'll give you an extra as if I dropped a homework, okay? So there's motivation to take this seriously and grow something amazing, okay? So, again, I'll post this, read through it, and come with questions about it on Wednesday. Otherwise, I'm going to dive into the class material today. Okay, today our learning objectives are as follows. We didn't quite finish homogeneous nucleation. We got really close. What we didn't talk about, we talked about nucleation, but now we have to talk about growth and transformation. So we'll start with that. Once that's done, we're going to do the exact same routine, but we're going to do it for heterogeneous nucleation this time and talk about the differences. And then if we have time, we'll talk about how melting alloys, when you solidify them, it can produce something called a dendritic structure, which is important for a lot of applications. And at the end, we might have time to get into Avrami equations for generalized transformations, okay? So we left off last time, and the last thing we covered is we came up with some slick equations that told us as a function of materials properties like enthalpy, how far you are below the melting temperature, that's the degree of supercooling, the surface energy. We could calculate the activation energy necessary to cause nucleation to happen, and we could also calculate the size of this nuclei, right? We did those last time. In this case, for gold, even though you already had supercooled it 230 degrees below what the phase diagram said, you still had to get a glob of particles 1.3 nanometers big. So that's lots of atoms that had to come together before it spontaneously keeps on growing. So some of these critical nuclei sizes can be fairly big, okay? All right, so once you form a nucleus, you're not done. The transformation is going to have to go from that nucleus. It's going to have to grow until it consumes all of the previous phase. So that's the rest of the growth and transformation. So the first thing we should know is, okay, how many stable nuclei will we have as a function of the activation energy and the temperature, right? So n star, that's the number of these stable nuclei that we have. We have an expression for it, and it is Arrhenius, right? N star, the number of these nuclei is going to be multiplied, it's going to be equal to a constant K1 multiplied by the exponential of the activation energy for nucleation divided by your thermal energy, okay? So at any given temperature, you could plug in T there and figure out how many nuclei should I have. Is it 1 or is it 1,000,000 or what is it? And this will spit out a number, right? Okay. You do have to know the constant K1, which is going to depend on your system ahead of time, okay? Quick thing to note here is that delta G itself, delta G star, if we go back to it up here, right here, it itself is a function of temperature. So you have something that is a function of temperature inside of an exponential with temperature in it. Delta G star depends on 1 over T squared. It's proportional to 1 over the temperature squared, right? So when you put that in there, into this expression, you get the opposite dependence that you normally see. Normally, an expression like the one underlined in blue says the higher the temperature, the more of something, right? We've seen that all semester long. The higher the temperature for diffusion, the faster the diffusion. The higher the temperature for creep, you get more creep. Here, you might be tempted to say, oh, the higher the temperature, the more stable nuclei I have. But that doesn't make sense, right? Because remember, you have your temperature where up here you're a liquid, and below that you're a solid from a thermodynamic standpoint. What we know to be the case is that the further down we go, the more and more nuclei we should have because the activation energy gets smaller and the critical size also gets smaller. So it can't be that getting it higher and higher in temperature gives you more nuclei. And the reason why it doesn't is because delta G itself depends on temperature, right? So that's why that makes sense. It has its own temperature dependence built into it. It's not a constant. It depends on temperature, okay? Now the next thing we have to know is once you have nuclei, something has to attach to them, right? And the rate at which you get things attaching to them, we're going to call that V sub D, right? Sometimes you can think of that as like drift velocity, right? The attachment velocity, they call it, V sub D, is also equal to a constant, this time K2. It's a different constant than before. And then this one is multiplied by the exponential of our negative QD, that's the activation energy for diffusion, divided by thermal energy. So that one has the proper temperature dependence like you'd expect. At higher temperatures, as you move up, you get faster and faster diffusion. So do you see there's a conflict setting up here? Your overall transformation, it's going to depend on one hand by VD, right? But it's also going to depend on the number of nuclei that can grow. So it's the rate at which each nuclei is growing, and it's going to be how many of them there are. And they depend on things differently with temperature. So you can see right away there's not going to be one right? It's not like always going to higher temperatures better or lower is better. There's going to be a sweet spot, right? There's going to be a temperature at which you get your maximum transformation because these two things have different temperature dependence. Can I answer any questions about that? Yeah, Eric?
What's K2?
K2 is just a constant, okay? These are things that you would analytically determine from experimental data. K1 and K2 are just constants, okay? So if we were to plot these two things, let's plot them on a scale versus temperature. So you're going to have something that looks like this. So this is, we'll just write rate. You could think of it as being proportional to the amount that's transformed. Up here is going to be temperature. If we draw the temperature where we expect it to happen thermodynamically, remember we call that T alpha beta. That's the temperature where the phase diagram said it should solidify, okay? We have two different effects in competition here. You've got this thing, N star, which you get more and more N star the lower and lower you go. So the rate would be increasing based off of N star. There's more critical nuclei. But your rate of attachment is going to be better and better the higher you go. So V sub D is going to be up there. And the total transformation is both of these put together, right? So when we put them together, the overall transformation might look something like that, okay? That doesn't yet account for growth, but that's critical nuclei and attachments, okay? So we'll call that N dot, the nucleation rate. The rate at which we are nucleating new particles, N dot is there. And you can see that it is associated with a temperature, right? This temperature right here is the temperature at which you're going to have the fastest nucleation. So for those of you that are growing salt and sugar and Epsom crystals and all sorts of things, think about controlling temperature, how it's possible for you to control the temperature of your solution. Because if you were to just try this randomly, you mix together your stuff and you let it loose, you might be down here. It might not be its fastest, its nucleation rate. So you would love to know what this is ahead of time and cause it to nucleate as fast as possible so that in 3 weeks from now, on the last day of class, you show up with a ginormous crystal and you get a wave and extra homework, which would be what the goal is, right? Okay? So your overall nucleation rate, N dot, that's N dt, right? The change in your nucleation as a function of time. It's going to be equal to A star times N star times V sub D. So A star is a constant. It represents the number of atoms that are near the surface. So remember, you've got your critical nuclei, and then your atoms out here that are going to attach to it, they have to diffuse over, but it's going to depend on how many of these atoms are surrounding it, how densely packed it is. That's what A star represents. And it's just another constant. It's another constant that we're going to use, okay? So you've got your overall expression looks something like that, okay? Okay, any questions on that? That is homogeneous nucleation. The only caveat I've got here in the notes here is that, remember, this treatment is completely, you can transfer it over to other shapes. The one I showed you in this class and last class was for spheres, right? But you could also do it for cubes or any other crazy shape you wanted. Okay, any questions? Okay, so let's switch gears and talk about heterogeneous nucleation. First off, where do we see heterogeneous nucleation? Anybody know of a good example of this? Is it industrially relevant to anything? Alan, you got a thought?
I was just thinking, like, condensation. Isn't that heterogeneous? Onto something?
That's a great point. Let's pull it up. So if we go to YouTube and you type in cloud seeding, anybody heard of cloud seeding before? Okay, cloud seeding. So how does cloud seeding work? Anybody want to try and explain it? Yep. Yeah, so we're not going to get audio coming through, so we'll have to just sort of explain it as we go. But how cloud seeding works is the clouds, if they, remember, in order for that nucleus to happen, in this case it's going from the vapor to the liquid phase. In the class we did liquid going to solid, but it's a similar kinetic problem, right? But as you go from those little molecules that are in the gas phase, you want them to turn into droplets maybe, right? And to make that happen, there's going to be an activation energy. I don't know if this video is going to play. There's an activation energy and there's a critical size they have to reach. And the temperature that you can't control, that Mother Nature put up in the air around you, is going to dictate whether or not these things happen. And it may not be fast enough for you. So what they do instead, Let's see if we can find a video of it. This is the worst animation ever. Where's the one I'm looking for? Here we go. All right. So instead, they literally take airplanes, they fly them through the clouds, and they have things. In this case, it looks sort of like they've got like phosphors burning behind them. There's lots of different materials which will seed clouding. You can use silver iodide. That's one of the more common ones. But I think they're using something phosphorus in this one. I've read about it somewhere. I'll look it up and tell you. But they literally have them dragging along the wings, spraying this chemical, little tiny particles. And the idea is that every single one of those tiny little particles will be a droplet of rain. Right? Does this seem like crazy? This seems crazy that actually works. This works, though. They can either fire into the sky with a gun, which they also do. They can do this, or they can start a fire. And in the Appalachians, they actually start fires with some regularity because it leads to cloud. It seeds the clouds. Those little particles in the air cause rain later on, which is pretty wild, right? So this is a perfect example of heterogeneous nucleation, because if it wasn't for those little droplets that you're starting automatically, they wouldn't start on their own. So there's whole countries, especially in the Middle East, there's whole research programs dedicated towards getting those clouds to give off their water by seeding it, okay? There's lots of other applications for this, though, right? If you've ever bought and eaten any sort of decent chocolate, that chocolate was made with seeding, right? So you can take the chocolate and you can melt it to the exact sweet spot where it should transform into the phase that you're interested in, but it's slow, and it's not guaranteed that you're going to get your phase because they're really close in temperature. Like a couple degrees will switch it to the wrong one. But if instead you take a little bit of seed crystal chocolate that is in the right phase, you can cause it to grow until you get all your chocolate to be the correct phase. It doesn't melt. It has that nice crisp snap. It's completely different than chocolate you just melt and pour into a mold. Sam?
Is that one whole crystal?
So if you started with a single chocolate seed crystal and you touched that surface and you did like I didn't bring my, I'll bring them next time. We have single crystals. We have this in my lab. You can touch the surface of that liquid and you can slowly draw it out. The idea being that it's hot in this lower temperature, and as you lower it out, it's in a colder temperature. So it's going to keep on crystallizing. It's not going to melt again. And if you slowly draw that out, you'll get a big single crystal of chocolate. In practice, that's not what Nestle and company are doing. They're polycrystalline. They take their chocolate in a liquid form, right? So they melt it in like a double broiler sort of thing. They take seed crystals, so just nice chocolate that has been tempered. They chop it up into tiny little pieces, or they grate it is even better. If you grate it, you get really small chunks. You pour that into the liquid. First off, it's going to lower the temperature because you're adding a solid, which is lower temperature than the liquid. So it's going to start solidifying anyways. And the places where it starts to solidify is next to the cold, perfect crystalline chunks, and then they grow. And you added a bunch of them. So it's not single. But you could. There's no reason you couldn't grow a big single crystal of chocolate. And I hope one of you will do that for the homework. I don't know if it's possible. It should be possible. Okay? Yes. If you come in with a single crystal of chocolate, I don't care if it's the biggest one, I will drop an extra homework for you, but it's got to be single crystal. All right. Don't everybody do that, because I don't think it's going to actually work. I think you're going to get polycrystal. All right. So why do we care about this? It sounds like a lot of work. You have to have this little thing that you lower down. You have to pull it out really slowly. It's complicated. You don't even know if you have a single versus polycrystalline without doing additional tests on it afterwards. Why do we bother? The reason why we bother doing this is because you can have it happen at way, way lower degrees of supercooling, okay? So the gold example that we showed you from last class, where it went 230 degrees below its melting point, you better have a really perfect setup to achieve that, because any little flaw or imperfection is going to likely lead to heterogeneous nucleation instead, okay? So heterogeneous nucleation takes advantage of pre-existing surfaces or impurities. We already showed you this, that basically instead of it forming right in the middle of the solution, where now you have solid other than the liquid that it formed out of, instead it's going to form like on the domain wall on the side, or maybe on an impurity in the middle. It's going to grow on the side of it. And the reason it does that is because it changes the ratio of volume to surface area. Remember, that's what was stopping us before. The thing that was stopping us from growing things, volumetrically, free energy says this should be happening. The thing that was stopping it was the surface energy. But when you grow on the surface like that, it changes the ratio of volume to surface area, and it makes it favorable. It gives you less surface area and more volume, okay? So the mathematics are basically the exact same. We just have to modify that surface energy to volume ratio, okay? One way that we do that is let's draw the interface here, okay? So this is our interface, okay? We're going to nucleate on top of this some sort of solid out of the liquid. So we can do a quick force diagram on this thing. And there's going to be a series of different energies. You've got the energy right here, which is going to be the surface energy between your interface and your liquid. You've got this energy right here, which is going to be the surface energy between the solid and the liquid. And then you've got this one right here, which will be the interface energy between your interface and your solid. Okay? So you have three different surface energies that come into play here. Right? These are things that you could measure or maybe look them up in a book. The gamma IL, gamma SI, and gamma SL. You could look those up. And if you know those, then we could calculate theta, right? So theta will be your contact angle. Sometimes they call it the wetting angle, okay? So this angle right here, that is your wetting angle. And anybody who's put a little droplet of water on something that's hydrophobic has seen that these things form. In some cases, it looks like it's a perfect sphere, like it's a really, really high wetting angle, right? Other times it doesn't, other way around, it's low wetting. Other times it's very high wetting where it actually smears out. So that angle that you see when you put these little drops on things, it totally depends on those three surface energies, okay? So if you know those three surface energies, you can calculate theta, which will be your wetting angle. Why do we care about that? Because once you know your wetting angle, you can calculate S of theta, this term here. And all that is somebody did the geometry for you, and they basically said, if this is a perfect, sphere, you can take any sort of spherical cap of that, and this will tell you the surface area to volume ratio, right? So that S of theta, if you look at our expressions from before, these things look the exact same as before for homogeneous nucleation. The only difference is that they've been modified by this S of theta, right? S of theta is a number between 0 and 1. In worst case scenario, you have homogeneous nucleation. If S equals 1, S of theta equals 1, then your wetting angle is so severe that it's like a perfect sphere, you don't get any benefit of heterogeneous nucleation. But it can also be less than 1. It can go all the way down to 0. And that's going to give you a big reduction in your activation energy for nucleation. Like, look at your delta G star expression. It's the same as before, except it's multiplied by a number between 0 and 1. So you can get huge reductions in your activation energy that you need for nucleation to happen. Okay? So quick question. Does this change your critical radii? The size of your thing, does it change? It's the same, right? This expression right here is unchanged. That R star, if we go back up, so it's negative 2 times gamma over the change in free energy on a per volume basis. That's exactly what we had before. Negative 2 times gamma over the change in free energy on a per volumetric basis. So the size doesn't change. It's that the activation energy goes down, right? So if we were going to plot that, this was our plot from before. How would we modify this plot? Let's sketch it again. Okay? If we were going to modify that, it would now look like this. Again, plotting energy versus your particle size, R. Homogeneous might look like this. So this is homogeneous. Whereas heterogeneous is going to look like this. Okay? In other words, these both have the exact same R star value. They both have to reach that same size, but one has a much lower activation energy. So we would say that this is delta G star homo, and this is delta G star hetero. Okay? Any questions? Yeah.
Can you go back to the drawing you did with the interface and the solid and everything?
Yep.
I'm just a little confused. Like, what is gamma representing?
Gamma is a surface energy. But think, a surface is defined as 2 different phases, right? And we can count 3 different phases here. You've got your solid phase in green, You've got the red liquid phase, and you've got your interface. That could be like the crucible wall. That could be a fleck of dust. It could be whatever you want, right? But the point is, all three of those have different surface energies. And if you know those three surface energies, then you can do a force balance on it. You literally sum up the horizontal forces to be equal to 0. And that's what lets you calculate that theta value. Okay? Any questions on that? And then all it is after that, this formula here for S of theta, that's simply the formula for the cap of a sphere. And that cap, we could define it at different spots, right? It depends on what your wetting angle is. Maybe it's that much. Maybe it's just the very top. And that's going to change how much of a benefit you see from heterogeneous nucleation. So when you do something like cloud seeding to get rainwater, you'd want to pick something that, you'd want to choose the surface energy of the material that you use. First off, it's cheap. It's non-toxic, right? It's okay if you litter it over all of a bunch of population, right? It's not going to kill people or mess up anything. But also gives you something that looks the most like a spherical cap, because that's going to give you the biggest benefit. Okay? All right. So let's see. So how's that going to change our picture for nucleation, right? We showed you nucleation at the start of this class. Remember, we said the following about nucleation. We said that we'll just write the rate down here, and this is temperature. And again, this is our temperature at which thermodynamics says it ought to happen. And we decided that under homogeneous conditions, there is a temperature where it is optimal, right? So we would say that there is a temperature right there where N dot homogeneous is maximized, okay? How's that going to look differently for heterogeneous? How ought we to modify that? Well, we could go back up and we'd say, okay, let's go back to our expressions for that. When we calculated capital N dot, right, that's the nucleation rate, it depended on a bunch of constants. Let's assume those constants are the same, right? Fair assumption, same material. All we've done is change the nucleation type. Then you've got your activation energy and diffusion, right? So diffusion should be the exact same, but instead of doing negative delta G star, remember that now this, in the case of heterogeneous, it includes that S of theta term, which is just between 0 and 1. So it's going to look the exact same, except we're lowering the activation energy, right? So what we should see in these terms is we should see that heterogeneous nucleation should look like that. Heterogeneous. Okay? You should get faster rates at a smaller amount of undercooling if you do heterogeneous nucleation. Yeah? No, let me fix that. So it should look like that. All other things equal, it should be the same rate. It should just happen at a different temperature. Okay? I guess technically it should be actually a little bit better because you're at a higher temperature, your diffusion's a little bit better, so it actually should be a little bit faster. The point is you don't have to supercool it like crazy. I have a demo where we do supercooled water, and I went to bring it today and it was not solid yet. It didn't work, so I didn't bring it, so I will have to bring it next time. I put it in the freezer this morning and it wasn't long enough. But essentially, if you take like a water bottle and you have it below that degree of supercooling, it could be in this region where it's up here and your nucleation rate is really slow or even essentially 0, which means you can supercool it further. But as soon as you add a heterogeneous site, it will spontaneously crystallize. In fact, let's just watch a video and I'll bring that on class on Friday. Okay, so it works best if you use Fiji water for reasons that depend on the purity of the water. If you use tap water, it's full of ions. What are ions going to serve as? Heterogeneous nucleation sites. So that's going to cause it to freeze really easily. So this guy took a Fiji water bottle, which is typically distilled. It's more pure. They put it in the freezer. You have to let it, if you let it sit too long, it will eventually freeze, depending on how cold your freezer is. Oftentimes you put it in there, he's putting it directly on that metal plate, which is usually, it won't work if you do that because the metal plate's typically a lot colder than the air. and so that's going to serve as a site that is much colder than the air around it. So if you put it in a thermos, it tends to work better, right? Put this thing inside of a thermos, and then it sort of slowly, from all directions, this cold temperature comes in. If you let that sit for apparently longer than 3 hours, like I tried this morning, and come back to it, so let's see what he does. He's going to take this out. He's going to grab one of these things, and if you're really gentle, you can't, like we walk it over here, and you see that very clearly a liquid. You can't jostle it too much, though. But then if you take that, and you provide it just a little bit of energy, a heterogeneous nucleation site, it's going to spontaneously crystallize. So if he takes it, I think he's going to pound it on the table or something, and you'll see it. See how that grows? That's ice forming right there. So again, it's at no point was it not thermodynamically favorable for that to happen. It's just that it had that surface energy that it couldn't quite overcome. So little ice particles were forming, and then they were just dissolving again because it didn't have enough to get over that hump. But as soon as you gave it something to get it started, you could actually measure the rate at which it transforms, right? Which is exactly what we're getting at, is that rates of transformation, okay? In that case, it's a little shock wave that did it, okay? So there's nucleation rate, and then there's growth. And these obey slightly different kinetics. The growth rate stops caring about the number of nuclei. It just says, all right, however many nuclei you have, they just have to grow. And so it's exactly what we saw before. A growth rate should depend on just your diffusion coefficient. Yeah, Chase?
So with something like water, is it easy, like not easy, but like could you achieve a temperature where it actually starts to slow down again and it gets like really, really slow when it's that cold? Or is that pretty...
When you say slow down the rate of transformation? Yeah. Yeah, if you did that experiment and you set your freezer to different settings, all of them below 0, right? I imagine that if you did that experiment with those bottles, you'd see different rates. For sure, right? Because higher temperatures, so this might be counterintuitive. You might think if I'm only a couple degrees below the 0 Celsius, and I do the experiment, it should go really slow because I don't have any nuclei. But remember, that's where you have faster diffusion. And then if you go really, really far below, you might think, oh, great, I'm going to have lots of critical nuclei, but there you don't have good diffusion. So you should see a temperature where you get some maximum rate. I have no idea if you could actually do that on water. It'd be a sweet experiment. Okay? Any questions? Okay. So remember that your total transformation doesn't depend on just nucleation, but rather it depends on nucleation and growth. So if we were to plot this one more time, the total rate on the x-axis versus temperature, we know that nucleation looks something like this, but growth looks something like that. And your overall transformation is going to multiply those two curves together. Anytime you take two exponentials and you multiply them, you get something that kind of looks like that. So that's going to be your overall, I'm going to put T dot, transformation rate. Transformation rate. And it's the product of N dot and G dot. Oh, I should switch those. N dot is going to be right there, and G dot is going to be up there. It's going to be the product of both the rate at which you can nucleate new phases and the rate at which they're growing. Yeah, Abby? Okay, so we're not going to get way into it in this class, but the main idea is this, that you have, okay, so this is where we derived V sub D, the attachment rate. It basically had to do with the rate at which particles near that thing can diffuse and attach themselves. Whereas growth is slightly different kinetics because remember from last chapter we talked about grains growing 2 chapters ago? We showed you how the small ones shrink and the big ones get bigger. Those are slightly different kinetics because it's all in the solid phase now and yet they're growing. So they're slightly different kinetics is the main thing. We're going to model them as both having their dependences on the diffusion activation energy, but they'd have different constants, K2 versus down here we called it just C. But very similar kinetics, okay? Any questions so far on transformation rates, on the rate at which we're transforming? Instead of talking about rates, it's sometimes more useful to talk about things in how long did it take before it was complete, right? So times to completion. And the transformation rate is going to be inversely proportional to the time till completion, right? A faster rate, a shorter time to completion. So if we plot this, right, this now leads us to the whole point of this chapter, which is TTT curves, time, temperature, transformation curves. So on the x-axis, we're going to have time. The y-axis is going to be temperature. And then what we're going to show on this plot is a series of different transformations, right? So you can have a curve like this, curve like that, curve like that. Now you'll notice that this looks like a C-shaped curve. It looks like the letter C. The reason why it is because transformation rate is going to be inversely proportional to the time to completion. Sometimes they write that 0.5, meaning the time it takes to be half completed, right? A faster rate, a shorter time. So what you're seeing here is lines that represent 0% transformed, 50% transformed, and 100% transformed. So just like there was one temperature at which we saw the maximum nucleation and growth rates, right? Up here we saw one temperature where it happens the very fastest. That means that if you think about this not in terms of rate, but instead you think about it time until completion, there will be one temperature where it occurs at the shortest period of time, right? That will happen the very fastest. Everybody with me? Why do we care about this? Because think what this lets us do now. Up here, we had our temperature at which this T alpha beta. If you cool down from T alpha beta and you cool down sufficiently fast enough, where you cool it down, say, at that rate, where time is changing, but you drop that temperature really fast, you never touch that line. We call that the nose of the TTT curve, right? Because it looks like a nose sticking out. If you never touch that nose of the TTT curve, then you don't get transformation, right? Instead, you form a metastable phase, right? If this was liquid and solid again, that liquid, you wanted to turn into a solid, but if you quench it fast enough, you reach a region where you now have metastable liquid. It should not be stable at these temperatures, but it is for a really long time. This is on a log scale where you plot this. So that might be years or centuries, right? For the case of your diamond on your diamond ring, you've quenched it so quickly that now you have diamond, which should not exist. It's metastable. And if you give it long enough, it will start to turn into graphite, right? So this is useful because blacksmiths use this all the time. When they quench their swords in all sorts of different medium, blood or oil or water or whatever the different things they use, they actually did. But there was a story that said they used to stab slaves. That turned out to not be true. That was like an April Fool's joke that everyone thought was for real for a long time, but it's not real. Okay? So as you cool it down at different rates, you're going to get different phases forming. If you quench it in water, which is a really aggressive quenching medium, then you might get a metastable phase. Whereas if you cool it in oil, then it might go through the middle of that TTT diagram. So what happens? Let's say you take it out of the furnace and you immediately put it in a separate furnace. If you quench it down to here and then you put it in a furnace out to here, you still get 100% transformation. It's no different than if you took it here and quenched it across that line. In either case, it's going to start to transform the second it touches that line. It's going to continue transforming all the way until it's 100% transformed. Okay? Any questions so far on TTT curves? Okay? We're going to come back to those at the latter part of this chapter when we talk about steels, because these are super important for steels, and you can use them to get lots of different types of steels. Even though the composition is the exact same, it's all whatever 10% carbon or whatever it is, you can get wildly different properties depending on how it was quenched. Andrew?
So in the process of blacksmithing, they often temper after they quench it. Wouldn't that be the same thing as not quenching at all, just letting it go?
Yeah. So there's more to this that I haven't shown you yet. We're gonna add some more details to this that will make it clear what they're doing. It's called tempered martensite. We'll come back to it. So first, let's talk about how just general things cool. What does a microstructure look like? If you take any metal ingot, right, and you heat it up, and then you just take it out of the furnace and set it on a countertop, it will start to solidify. And the way it's going to solidify is from the outsides in, because outside of the mold is where it's cold. It's in a room which, relative to the molten liquid, it's cold outside of the crucible. So if you were to look at this thing, there is a temperature gradient across this. We could draw the temperature gradient as going like that, where that's, that's higher temperature, right? It's cold out here, it's hot in the center, and so you've got this temperature gradient all through your crucible. What that leads to is columnar growth. You get this region right on the surface where it touches the cold crucible if you poured it into there, and it forms little equiaxed grains. But then there's a temperature gradient, and the grains grow along the temperature gradient. So literally you can see that. If you zoom in and look at these things, you can see big, long grains growing along the temperature gradient through this thing, right? Is that good or bad for engineering properties? What do you think? Do you want that? Can you use that? Is it terrible? I guess the answer is like it depends. Like, can you think of an application where you want a huge difference in strength, like anisotropy in the middle of your alloy? Not typically. We typically want things to be more uniform than this, but if you pour it into a mold, that's what's going to happen if there's a temperature gradient. So because of that, people have tried all sorts of things to control the temperature gradient when you do this. And what that can lead to is the dendrite structure, dendritic growth, okay? So this is actually pretty interesting. Dendritic growth, you have to have flash to see this, so we'll see how long I'll be able to use this demo. Flash is dying. So we'll tell it to allow it this time. And we've got flash here, right? So we're going to do two scenarios. You've got two scenarios. In one case, so this is your solid. The solid would be on the left-hand side, and over on the right would represent the temperature of your liquid. So in one case, the liquid is much hotter than the crucible, right? So you had a cold crucible, you poured your molten metal into it. Let's do that one first. So now you've got hot liquid, cold solid, okay? As you start to solidify, think about what happens. The first thing is that there's random temperature fluctuations, and at one spot there, it might be a little bit colder than the area around it. And so that little region is going to extend out into the liquid. It's going to form a solid, and it's going to extend out into the liquid. But think what that's doing. In terms of temperature, as it extends out into the liquid, it's going up in temperature. So that little, what they're calling a protuberance, is going to melt again because it went up in temperature. It's moving into a region that's hotter, so it's going to melt again. And so that thing, even though it forms momentarily, it's going to disappear because it went into a region, so it just melts again. In other words, this whole thing's going to sort of grow nice and uniformly. That leads to these columnar growth that you saw, right? Now, the other scenario is this. In this case, you heated your crucible up quite hot, and your material is such that as it solidifies, it takes energy, which is most things. Most things, as they solidify, it requires energy. That's why steam burns are so bad. The steam burns and it has to take energy. Oh, other way around, sorry. It has to take energy, so it's going to be cooling itself off as it solidifies. So that leads to a temperature gradient that's relatively hot, your crucible is, but your liquid's less hot as it solidifies. So now think what happens. As a protuberance forms, a little bit of solid, so this little piece of solid forms because of slight temperature fluctuations. So as that thing forms, it's extending out into the liquid, which is going down in temperature. So it's not going to melt again. Instead, it's going to be stable. This is a stable imperfection. This is the start of the dendrite. And as it grows, the same thing happens off of the sides of it. They're going to extend outwards where it's slightly cooler. So they're going to keep on growing. And so you end up with these dendritic structures that grow through your material, right? So you see this all the time in steels. Dendritic, steels, right? Where you can see them all the way through your metals. You've got these dendrites that form. And so the rate, like the size of these things, it's going to all depend on your processing conditions. How tightly did you control temperature? What was the enthalpy of cooling, right? How much energy did it take as it went from a liquid to a solid? That's going to change the temperature. But getting these things, you shouldn't be surprised that you see them. Now, how are they going to modify your mechanical properties? What do you think? Are they going to make it more ductile or less ductile? Harder or softer? They're going to make it harder. Why? Yeah, it's like one of the classic things I hope you take out of this class. If you do anything that makes it harder for a dislocation to move through this material, you made it harder and less ductile, right? So these steels are going to be much less ductile than if you grew those really columnar grains in them, which are going to be more ductile, but at the expense of being much weaker, okay? All right. So let's see. That's not, by the way, these look like snowflakes, but snowflakes grow by a different thing. You can read about it. Okay, this brings us, we got 5 minutes left. Let's introduce the Avrami equation. So the Avrami equation was actually discovered simultaneously by 3 Americans and a Russian at the same time. And it took them a few years to agree that they all discovered it basically at the same time. So the actual name is like AVJK or something. Avrami equation. But they only call it Avrami, like the first guy, but realize there's like 4 other people that probably deserve credit. The JMAK, and the K was the Russian, Kolmogorov, right? So essentially, they all sort of concurrently realized we can model transformation if we have the right mathematical expression. They know the following. They know that it's logarithmic and that things start to transform. And when they start to transform, if you look at your percent, say, for example, in crystallization of polymer, it starts to transform really slowly. The rate is slow. Then once it's transforming, it reaches a maximum rate, like the slope here is at the highest. And then once it transforms, it starts to slow down again. And basically, this describes the vast majority of transformations, right? So all you need to model this is you need a mathematical expression that looks like that looks like an S. So what do you have? What looks like an S? You can do it with exponentials, right? So the Avrami equation is as follows. Y, the percent transformed, right? That's this guy. Percent crystallized or transformed, right? Y is going to be equal to 1 minus the exponential, exponential of negative k multiplied by time raised to the n, where k and n are just constants. They're just fitting constants. Okay? So for your system, you could figure out k and n, and then if you know those, you could figure out for any given time, whether it's been cooling down for 5 minutes or 10 minutes or whatever, you could calculate how far transformed it is. Because this sort of S-shaped curve, what's called a sigmoidal curve, fits the actual data. Okay? Now you can see also here in polymer crystallization, what is the rate doing when you change temperature? If you do polymer crystallization at a low temperature, it might take a really long time. This is 100 minutes, right? It's barely even started to transform after 100 minutes. But you take that exact same polymer batch and you heat it up over here to 135, and it's finished by, 30 minutes. It's already done, okay? So these things are temperature dependent. These kinetic processes are temperature dependent, okay? So we're essentially out of time. Let's see if I want to say something else before we move on. I think that's all we want to cover today. Can I answer any questions about Avrami kinetics or anything we've discussed today? So to answer questions about this, if I gave you a plot like this, yeah, how about that? If I gave you a plot like this, and I said, now I want you to tell me how long will it take for a material at 125 degrees to be 75% transformed, what would be the approach? Yeah, so basically these constants right here, these things are temperature dependent. So if I had given you a line of 125 degrees, you could just fit it, and once you fit it with k and n, you'd be good to go. You'd plug in 0.75 for 75% transformed. You know k, you know n, you could solve for time. If I didn't give you that curve, but I gave you this, what would you do instead? What would you do? Well, you could probably plot, as a function of temperature, you could plot k and n and get some sort of trend. This might represent 135 degrees. This one represented 119 degrees. So you could do some sort of linear interpolation to figure out the rate between them. And maybe linear is not even the best model. It might be exponential. But you could see that by looking at the data points. Was that your question, Andrew? Okay. So there'll be some sort of question about that on the final. Even though this homework won't give you a chance to work through these, on homework 10 I'll give you a few of those so you get practice on it. Okay, that's it for today.